This is pre-calc. This is the note outline 5.1. This will be day 1. We will be taking 2 days on this. We are skipping over 5.3. Second hour made the executive decision for you guys and said, hey, we will solve trig identities or solve trig equations or functions after we do some more identities. So we're going to try keeping the identities to group together and then come back and say, hey, when does sine of theta equal 1/2? And then we have to list all of the angles, degrees, or radians that would have to make that true. So today we're just going to deal with another set of identities. This time it's the sum and difference identities. So now we're going to be able to add and subtract angles inside of trig functions, sine, cosine, and tangent. And so what we have are 6 of them, but there are really only 3 of them. So when you guys write these on the back of your unit circle, you actually should be able to get away with just putting a plus or minus, as in a plus-minus sign with a plus sign with a minus sign underneath it, vice versa, when you write these. Because if you notice, they are the same. Like this cosine of alpha plus beta. It's got a minus sign on this one. But when you go over here, it's alpha minus beta. Now it turns to a positive sign. Otherwise, everything else is the same. Sine gets to keep the sign. So when it's positive between the angles, it's positive between the functions. When it's negative, it's negative. Tangent, positive, positive on top, goes to minus on the bottom. When it's negative between the angles, it's negative up top, positive below. Okay, so it just switches from one to the other. The key that I like to think of is sine keeps the sign, cosine switches. Okay, so that's just kind of how I remember these things. So notice there is a structural difference between sine and cosine, the sum and difference, both of them. Cosine is cosine, cosine, sine, sine. Versus sine is sine, cosine, cosine, sine. And tangent is a tangent plus a tangent over 1 minus tangent, tangent. That doesn't change except for the signs. Now, what we're going to do, the first thing up, is we are going to evaluate angles that are not actually on our unit circle. I have one that's in degrees, I have one that's in radians. There are a few steps up above here, and those steps would actually more lend itself to the radians here. But, so not sine, degrees are easier to work with. We're really comfortable with adding and subtracting numbers versus fractions with pi in it. So we're going to skip over the steps right now and talk about just the cosine of 15 degrees. The whole idea of the sum and difference identities is to come up with a way to get to the angle in question, 15 degrees, by adding or subtracting known angles. So what known angles do you guys know of that could get us to a 15? 45 and 30. You would have to do what with those, though? You would have to subtract. So 45 minus 30. So if I took cosine of 45 minus 30, would that be cosine of 15? Sorry, it went off the screen up there. Now, I'm assuming everybody should understand that 45 minus 30 is not the only way to get to 15 degrees.
Yeah.
What else could I use? 30 minus 15. That's correct. Guys, listen to this. This is important. 30 minus 15 also works. But 15 is an angle I don't know. So therefore, I will not use 15. Now, quick, could I use 135?
Yes.
And what? Minus 120. Could I use 150 minus 135? Okay, so there's multiple choices here. But I personally would choose stuff that has nice angles. The nice angles, guys, are the ones that are in the first quadrant, aka the first example that we just came up with. So I'm going to take away the second one. And now I'm going to proceed. I'm going to proceed to look at cosine difference, 45 minus 30, and I'm going to split it up. I'm going to expand it. So you go to your formulas above, cosine, subtraction, here it is. So it becomes cosine, cosine, plus sine, sine, or alpha, then beta, or 45, then 30. So this becomes cosine 45, cosine 30, plus sine 45, sine 30. Here's the cool thing. Can you guys tell me what the value of cosine of 45 is? Yes. Cosine of 30? Yes. Take your unit circles out. Now I'm going to replace all of these with their respective values. You take your unit circle. What's cosine of 45? Square root of 2 over 2. What's the cosine of 30? Square root of 3 over 2. Good. Sine of 45? Square root of 2 over 2. And sine of what? 30? 1/2. Now what happens when I multiply a square root of 2 times a square root of 3?
Oh.
Yes. 2 times 2? 2 times 2?
4.
What is the 1 times square root of 2? Over? They have common denominators. Let's put these together. Now wait a minute. Question that comes up. Can I take a square root of 6 and add it to a square root of 2?
No.
You can't. So you got to keep them separated. So, yes. Square root of 2, 6 plus square root of 2 all over. And there's your answer. Now, we're going to do this. We're going to do the same process, guys. This time with sine of 5 pi over 12. First of all, you look at 5 pi over 12 and you're like, hey, that's a pi over 12. I don't have pi's of 12 on my unit circle. So that's kind of a giveaway that to find an exact answer, I can't leave it like this. So I'm going to try using the sum and difference. How can I add two angles to get to 5 pi over 12? Now some of us might be inclined to say, I'll just switch that to degrees, makes it pretty easy then. I'm going to say, no, we're not. We're going to keep this in radians. And so I came up with these 5 steps right here, 4 steps, sorry, where I want you guys to get a common denominator of the known angles that we like to use. Guys, think back to degrees. When we talked about degrees, I had a 45, I had a 30, I had a 60, we may have done a 90, we may have done a 180. Okay? There's like 5 angles that you would add or subtract together. Just take their radian measures, their counterparts, and write those down. Like pi over 6, pi over 4, pi over 3, pi over 2, and pi. Those are the 5 main angles that every other angle on our unit circle is made up of. Can you guys agree with those? That's 30, 45, 60, 90, and pi. Or 180, sorry. Everything else is made from those. But take a look. Pi is really pi over 1. There's a reason why I chose this to be a pi over 12. Every single one of these numbers all go into 12. So therefore, I'm going to be able to make this angle from these. But to get these to be the same, I need to get them to have common denominators. That's step number one. Step number one says make them common denominators. So I'm going to go through and multiply them by their missing parts. 6 has to be multiplied by, so it's 2 over 2. Next one. Next one. Next. Boom. So therefore, now I'm left with 2 pi over 12, 3 pi over 12, 4 pi over 12, 6 pi over 12, and 12 pi over 12. Can you guys somehow formulate a way to get 5 pi over 12? Yeah, 2 pi over 12 plus 3 pi over 12. Can I just add these two together? Got it. I like that. Not necessarily the only way, but I think it's the easiest way. So I'm going to go here and say, hey, that's the same as the sine of 2 pi over 12 plus 3 pi over 12. And if I do this, these are equivalent functions, yes? They mean the same thing. Now notice in step 2, it says reduce it back to the known angles. Well, first of all, I don't know pi's of 12 either, so why would I leave it as 2 pi over 12? Change it back to?
Pi over 6.
Yeah, pi over 6 plus?
Pi over 4.
Pi over 4. You know those ones. Now, it's sine addition, which means changes to what expansion? Sine pi over 6 cosine pi over 4. Keeps the sine plus cosine pi over 6 sine pi over 4. Can you evaluate each one of those functions? I would hope so. So now, I'm going to evaluate what sine of pi over 6. Go to your unit circle, pi over 6. What's the sine? 1/2. Cosine of pi over 4? Square root of 2 over 2. Cosine of pi over 6. And sine of pi over 4. Square root of 2 over 2. Well, hey, wait a minute. Doesn't that look a lot like what we just did?
Yes.
Interesting. What's 1 times the square root of 2? Over 4 plus square root of 6 over 4. Again, I can't really officially put those two together, except for just getting the common denominator. It's the square root of 2 plus square root of 6 over 4, which is the exact same answer as the blue over there as a cosine of 15. Think of it, guys. The unit circle, the biggest number is 1, the smallest number is -1, and it goes back and forth, back and forth, back and forth, right? So therefore, I'm going to use the same exact numbers a lot. I'm just got to watch my signs. Are they positives? Are they negatives? Think about it. If we're using 45s, 30s, and 60s, you're going to get the same exact ratios a lot of the time. So you guys seen how I'm just going to get common denominators, and then it actually is very simple, just like the degrees. So let's try it into a little bit more of a word problem. And the word problem is just there to confuse you. But if you actually read it, took your time to digest what it's saying, it's not that bad. So, it says an alternating current I in amperes in a circuit can be found after t seconds using I equals 2 times the quantity of sine of 285 t, where 285 is in degrees. So they didn't put the little degree symbol in there. They're telling you, though, it's definitely 285 degrees. Two parts. A, I want you to rewrite the formula in terms of the difference, means subtraction, of two angles. And then B, I want you to use this difference identity to find the exact current after 1 second. So in part A, does it want you to change the formula drastically? No. It wants you to take the angle and write it as two angles being subtracted. What's the angle? 285. So am I going to change anything but 285?
No.
No. So if I had to write part A down, I have to start off with I equals what? 2.
Sine of 285.
Not sine of 285 anymore.
Okay.
I'm going to have some angles in here. And then T, right? But what does sine of 285 need to be changed to? It has to be switched to two angles. But I can't change the value. So, what's an option that I can change this to two angles? What two angles make up 285?
Oh.
330 and 45.
330
Minus 45.
minus 45. Does that work?
Yes.
Is that the only option?
No.
300 minus 15. It's an option, but do you know 15? No. 330 and 45 are both on my unit circle. I'm okay with those. 15 is not on my unit circle. Not okay with that. What else? Is there any others?
315 minus 30.
315 minus 30. That's another option.
You just read my mind.
We're going to go with this one because this was the first one said. Now, part B. Part B says use that difference to actually find the exact value of the current after 1 second. So, does 2 go away?
No.
Does the sine of 330 minus 45 go away?
Well, Dutch, can you switch them in now?
Right, it's going to go away, but we're going to switch it to its expanded version. Does t go away?
No.
Not officially. What does t become?
1.
Becomes a 1, and 1 times anything is
1.
that thing. So you don't have to write 1 anymore after this. Sine of 330 minus 45 will become sine of...
330, so square root.
No, we'll do that next step. So sine of 330, cosine 45, plus or minus, minus because it keeps the sign, cosine
330.
sine
45.
45. Can you evaluate all of those pieces? Does 2 go away? No, 2 still didn't go away. I got to leave them out front. But inside, I can take away all of those pieces and multiply them together, right? Kind of looks like a weird box there, doesn't it? Oops. There, that better?
Perfect.
Awesome. Now, what's the sine of 330?
Square root 3 over 2.
Mm-mm.
Negative 1/2.
Negative 1/2. 330 degrees has a 30-degree reference angle.
Oh, yeah.
And that 30-degree reference angle would be sine of 30, which would be 1/2, but it's in the 4th quadrant, which means it's negative. Cosine of 45. Square root of 2 over 2. Cosine of 330. Square root of 3 over 2. Is that supposed to be negative or positive? Positive. 4th quadrant, cosine's positive. And sine of 45?
Square root of 2 over 2.
Square root of 2 over 2. Well, what the heck? These are all the same numbers as last time.
Yeah.
Negative times a positive will be,
Negative.
so that's a negative square root of 2 over 4? minus square root of 6 over 4, which would lead us to 2 times negative square root of 2 minus the square root of 6 all over 4 and that. And now can I bring 2 in? Now remember, 2 is really 2 over 1. So I should probably distribute across top, right? Or, what's on the bottom of that fraction? There's a 4. Is there a 2 in that 4? So if I cancel this 2 out, cancel the 4 and make it a 2, I'll have negative square root of 2 minus the square root of 6 all over 2. Boom. And therefore we have an answer. Guys, these are exact answers. I realize I forgot to do something with you guys. We can do that with this problem. These are the exact answers. They have a decimal answer, right? So take your calculators out, guys. Take negative square root of 2 minus square root of 6 and divide all that by 2. What do you get? Negative 9.7? Or negative 9.7? I'm not sure. 0.97. 0.97. Could be. For those using a one-step type calculator, it's going to be interesting. You got to make sure you put this in right. Those who are working with calculators that you can group stuff and see it, makes it a lot easier. Right now, I'm just asking you to evaluate the square roots. It doesn't matter.
What do you think it was?
I got negative 1.9.
Yeah, I got negative 2.6.
Got negative 4.
Okay, we all got different answers. So, make sure, right now, everyone relax. If you are not using the gray calculators, so you're using one that you can actually see what you're typing, put it negative. Put a square root, 2. And your parentheses, whatever you have to do, minus square root of 6, and your parentheses again, if you need to. Hit enter.
Oh.
Now divide that answer by 2.
Still got negative 1.9. What are you supposed to get?
I don't know what I'm not sure what we're supposed to get.
I got 0.5.
So hold on. Okay, I'm getting a negative 1.93.
Yep.
Now, make sure that you guys are in degrees on your calculator. And I want you guys to do the sine of 285. Do you get the same answer?
No.
Are you in degrees?
Yes.
Oh, hold on. And then multiply it by 2. And do you get the same answer?
Yes.
All right. So I'm showing you guys that the answer that we get is the same. Where this is an exact answer, this would be called the approximation. So you guys could check these things on your calculator, but I still need to see all of this. We got 2 examples left. They're going to go fairly quick. Are you guys ready for these?
Let's go.
Let's do this. They look like they're complicated, but I want you guys to tell me the exact value of cosine of 7 pi over 8 times cosine 5 pi over 24 plus sine of 7 pi over 8 times sine of 5 pi over 24. Now, a giveaway here, there's a couple of them, to know that something's not right, is it's asking you to do 7 pi over 8. Nowhere on your unit circle do you have pi's of 8. Or pi's of 24 for crying out loud. So therefore,
Can't do it.
something's up. Second giveaway, guys, is the fact that you have a cosine times a cosine plus a sine times a sine. You'd be like, hey, isn't that one of my formulas that was expanded? Couldn't I bring it back and write it as a single value? Which one has a cosine, cosine, sine, sine? The difference of cosine because the signs change. So this really means that it should be cosine of
7 pi over 8.
minus
Minus cosine. Or sine.
Minus 5.
5 pi.
minus 5 pi over 24. Question then, can you get a common denominator? Common denominator is 24. So 3, 3, which leads us to cosine of 21 pi over 24 minus 5 pi over 24, which is cosine then of 16 pi over 24. Wait a minute, can I reduce that? What divides into top and bottom? 8. So this becomes cosine of 2 pi over 3? Wait a minute, is 2 pi over 3 on my unit circle? So if I go to 2/3 pi and look at the cosine value, it tells me it is -1/2, done. It's pattern recognition. You need to realize one way and the other way. Last example, last problem. Tangent of 6x minus tangent of 7x divided by tangent 1. 1 plus tangent of 6x times tangent of 7x. Notice this has got x's in it. It's okay. The only formula that we have that has tangents in it is the tangent formula, right? So which one is this? The sum or the difference? The difference. So this all comes down to the tangent of 6x minus 7x. Oh, what is that? Those are like terms.
-1.
Negative x, right?
Yeah.
You're almost done. Tangent is like half of you guys in this room. It is what kind of function? Not one of those. Not that. Think back to your identities on the first 4 groups. Different word for different. Difference, the better word for this. Odd, yes. Tangent is odd, guys. Odd functions. The negative, if it's on the inside, gets to go to the
Outside.
so it becomes negative of tangent of x. And there is the most simplified version of it. Tomorrow we'll finish up the lesson. You guys have to do the worksheet that I'll hand out in a second, 1 through 8. Have a great day.